Okay, so I hope you guys downloaded this FileZilla. I want to show you a little bit about FileZilla, how you can actually use this FTP client when you want to upload or download files from an FTP server. So I will show my FileZilla. So you can download here. The download page here for macOS, for example, you can use this, or for other platforms, Linux or Windows, you can download it from here. And after you download, there's also a tutorial here that we put it there. So how you connect, you can define your host and username and password on your port. Usually it's 22, your SSH port, and you're going to use your username and password to log in, for example, to our cluster. Or if you work with other companies like GeneWiz or I don't know, other sequencing companies, they might give you the host name, username and password, so you can connect to their accounts, your accounts in their server. So what I'm going to do now, I'm going to start FileZilla. Just to quickly introduce you how it works. I'm not gonna install the new version. So there are a couple options here. So you can write host name, username, and password and port here. Or I usually use like this. Oops, cancel. So I click here to the corner and I define my cluster here. Maybe I should exit from my Slack. It's distracting me. Okay, so you can define your cluster or any server you are going to use a lot, you can define them here. So how you're gonna do, you can click just new site and just write a name, my cluster, for example. And then you can choose the protocol. In our cluster, the protocol is SFTP, SSH File Transfer Protocol. So what you're gonna do, you're just going to write your host and the port. And the logon type will be normal. And you're going to write your cluster user and password. So if you are using other FTP servers, just ask them, like if it is SFTP, usually SFTP 99%. I've never seen FTP these days, but usually it's SFTP and the port will be 22. So we wrote this information there. So my cluster, for example, oops, I'm going to cancel this. I already did it for myself here. See host GHPCC UMass. You can either write this here, or if you don't write, default SSH port is 22. So you don't need to even write this. And then logon type normal, your user and password. And then when you connect, this is going to connect to the cluster. So when it is connected to the cluster, as you can see, you are in your home directory here. Okay, you are in your home. So home means 97W, my home. It's here. So, and I see my own files here in my home directory. So basically what you do here is you can change this side, your local computer. This side is your remote site, the cluster here in this case. So you can change to your Dropbox or wherever you want to download, upload files. For example, this is my downloads. So what I can do, or documents, what I can do, for example, I can choose the files in my cluster. For example, just to show you, I had a couple of examples here. For example, RNA-seq. I have some reads here. So these are FASTQ files. So you can use Shift to select multiple files with Shift, and then you can do drag and drop like this. So when you do this, it's going to start down here. See, this is going to be parallel. So I'm going to talk a lot about parallel today. So it is going to download all the files into my local drive. So usually what I do, I download these things into my laptop, And from my laptop, I can upload them to the cluster. But also cluster, in the cluster, we also have SFTP. So when you connect to the cluster, there is also a couple of commands here that I'm going to talk them later. But there are, like, for example, if you just directly copy files from GeneWiz to here, for example, you can use rsync or SFTP. Or there are a couple of things that I'm going to talk about that you can directly connect there and download the files from any other FTP server. These are important for you because you're going to download, upload files a lot. That's why you need to learn these. There are not easy ways to do that. You have to learn these from command line, most of the cases. But we are always looking new tools and programs. If we see any easy way, we will always upgrade our systems to make these things easy. Any questions about FTP? This is all, I think, about any questions about. You can ask questions anytime. Okay, if there are no questions, I'll move on to the session 2. Okay, today what we're gonna do is this.
Sorry, I do have
yep,
a question.
Of course.
I know I posted it on the chat. So how does this FileZilla differ from a CyberDoc?
Yeah, that's fine. You can use any FTP client. This is one example. CyberDoc is okay, or any other FTP clients you download are okay. The only thing you need to know, these interfaces are a little bit different, but they all ask you the same thing: host, username, password, and the port. That's all. When you have that information, then you're done. You can connect to those servers if they support FTP. So in our cluster, we support this FTP, so you can connect using this. Okay.
Thank you.
There's another question.
Okay.
So during my homework time, I looked at the FTP and I was not able to find where is my project folder.
Maybe you don't have. Do you think you have?
No, I have.
Okay.
I have an account for many years already, and there are some files there. But when I look at it, I just was not able to see how to find it.
So in this, like, for example, I'm going to show you mine project, UMW biocore, for example, will be our biocore servers project spaces here. See, my folders are here. So you can also check, let's check yours, for example. Just, it can be an example how the people can find that. So you can just ls project and UMW. Usually they are using, so your name was Alex. What was your name again? Sorry. Could you please talk? I'm going to see your name here.
Yeah, sure. I'm Alexander, but I'm just trying to remember. It is Alexander/Suvorov.
You don't have it here. So maybe they closed.
I think it does. So if you do UMA, instead of UMW,
sorry.
Yeah.
UMW is Worcester. I didn't know. Okay. UMA,
yeah,
Alexander.
Alex, yeah, you should come up.
Okay, you're here.
Yeah.
So I cannot, because I don't have a permission to see your directories. So if you go here, project Alexander Suvorov, either from here, you can just write like this, UMA Alexander. I cannot go now because I don't have the rights.
Okay. But does it mean that it is not this folder is not inside of my directory?
It is inside, means it's not in your home directory, because this is, you have to access this from the root. This is the root project, UMA Alexander Suvorov. But what you can do, there's, there was a homework that you learn how to use ln command, link. See, for example, there is space here in my screen. Can you see this is light blue? So this means it's a link. What I did to make it easier to access for me, see, this is the space is linked to project UMW biocore, my last name. See, so you can do that. What you can do, if you want it there in your home, you can go to your home. So this is my home, for example, And then you can do like this, ln minus s, this first, this project UMW biocore, for example, this director or whole, you can do all project space. And then you can say, for example, just here, you can give the full path, like AK97W. This is my full path. Change it with your own username. And then right here, for example, project. So if you give this name, for example, I'm going to do this and show you what happened. See, I have this project now and project UMW biocore. So when I do project now here, see, I'm in my project space. See, this is my project space. So this and this will be the same. So you can always use like this if you want it in your home.
Okay, thank you.
You're welcome. See, this is this project, and this will be the same. So this is, yeah, good question. Thank you. Okay, so let's go back about the cluster. So when you're doing stuff in the cluster, sometimes it's not going to work. Sometimes you're going to forget one space or one dash or something, and it will give you an error. So when something is not working there, just don't give up and try more, or ask us or ask your friends, other people around. So what we're going to do today is we are going to learn cluster and why we are using cluster, and what cluster means, how we're going to use the storage like you asked today, like what kind of storage we have, and how you can access to the head node and the child nodes, what head node is, what child node is, what job scheduler means, and how you submit a job, why you need to submit a job. We're going to answer lots of questions today. So today is extremely important for you. Even you don't use any applications we are going to show, if you learn this, how to do these things, how to run commands, well, then you can do many bioinformatics analysis yourself. So please focus today, do your homeworks, ask your questions to us, and repeat these pages a couple times to understand what's going on here. So why we are using clusters? The reason that when we have like many samples to analyze or process, we don't want to wait too much, because the software we are using today takes time. Like, for example, if you want to run RSAM to do transcript quantification, usually it takes hours, like 4 hours, 8 hours sometimes, according to the size of your initial reads. So if you don't want to wait like 8 hours per sample, like it's going to be, for example, if you have 100 samples, it's going to take like 800 hours. So if you use only one computer, because these are very costly software. Not all the software or programs we are using require this much time, but some programs like aligners or quantifiers, transcript quantifiers, take a lot of time. So that's why we use cluster computers. So clusters means that you're doing this biological experiments. It means you are using this kind of pipettes to do the same operation many times fast. So this is why we are using cluster. So it means that you are running your processes parallel, and you can get the results. For example, if whole pipeline finishes 8 hours in one sample, then whole pipeline might finish in 10 hours for 100 sample. So this is why we are using cluster, just to reduce the time. So when we say cluster, it means, when we say other HPCC or GHPCC, MGHPCC, they all mean the same. They're all cluster. HPCC, usually, in other universities, you're going to hear this again and again. So HPCC means high performance computing cluster. So GHPCC, that we have it here, and we are using in UMass, and a couple of other institutes are also using, like MIT, Harvard, Boston University. They are all in the same area in Holyoke. Our cluster is in Holyoke, And this is called Green High Performance Computing Cluster. That's why we say sometimes GHPCC, or Massachusetts Green High Performance Computing Cluster, MGHPCC. If you search this on Google, you can see the building and all the some information about MGHPCC. So in MGHPCC, we have like more than a petabyte storage. And this storage, same storage mounted to all these nodes. So in these nodes, we have around like 10K cores, means when you buy a laptop, for example, that laptop has 4 or 8 cores, for example. It means you can do 8 parallel operations at the same time. So in this case, we have like more than 10,000 cores in our cluster. But core means in one computer, you can have multiple cores. So when we say node is like your laptop, like one computer. And in one computer in our cluster, we have 8 cores. So we have like more than 1,000 computers, like 1,000 machines, servers we have there. So all those machines are called child nodes or nodes. And we also have a head node. So I just want you to understand what head node is and what child nodes are. You have to focus here, because when you use the head node, everybody is using the same head node. See, there are like multiple users. Today, I'm going to show you like how you can check how many people submitted a job to the cluster, or like you're going to do lots of checks before you start working on the cluster. But when you use the head node, you have to be aware that you're sharing the head node with other people. So when you're sharing this one computer, you cannot do high like operations, like running a process that requires high memory or requires multiple cores. So that's why head node is not for processing data. Head node is just to access to the child nodes, just to make sure that you're not running anything on the head node, but you are accessing the child node. I'm going to show you how. And then you are using all the operations, all data processing using a child node. And I'm going to show you today how. So before we talked about these things, but I'm going to repeat. So in our cluster, our storage organization is as following. So first we have our home space. So in your home space, it's located here in the cluster. It's /home, your username. This is your cluster username, or tilde. So it means this. So when you just do cd tilde, you're in your home. Oops. I'm printing working directory. I'm in my home now. And when I also, I can do this too. So ls home, this is going to work too. So the second storage is project space. You have /projects. See, this is not in your home. This is outside of your home, and you can access like this /project UMA or UMW. For people from Amherst, actually has different like prefix here. It starts with UMA and your name or your PI's name. The people in Worcester starts with W. And for Lowell, it's UML or Boston UMB. So we are sharing the same project and same nearline space. So here, your home space was limited to 50 gigabytes, but your project space is varied according to your lab. For example, Manuel's space is 40 terabytes in project, or in nearline, similar, around 40 terabytes. So if you're using a lot, you're increasing your space and paying a yearly fee. So just talk about people in HPCC, send an email to HPCC admins to ask more space if you need in the future. But if your lab is crowded, you're sharing the space too. So when you use the space, if you're not using the files anymore, back them up, and remove the files from there to create more space, because space is extremely expensive here in our cluster. So you don't want to keep unused files or the files that you can create in 8 hours, for example. Sometimes you delete all the intermediate files. When you do your rerun in Dolphin Next, it can create all the intermediate files in a couple hours. That's why we never keep any intermediate files unless we're going to use in a week or so, just to create more space and to be respectful to other people who are using the same space. And also we have this nearline space. This space is cheaper than projects, and the speed wise they are comparable. So I suggest you to ask more nearline space than project space, but the same. So you're gonna share there too. So, and this starts with NL. See, /NL UMW, again, your name or PI's name. And we process the data in both sites. So it's okay for us. The speed is not too different. So again, we have a couple of caution here. So we do not use the head node to process big data. We use the cluster nodes to process it. How do we reach the node? So we're going to learn this today. First, let's connect to the, you can actually repeat these things when I'm talking, and I'll give you more time when you're doing the rest of the things. But I want you to introduce a couple of things now, and then I'll leave you. You're going to do the things yourself, and then I will go over them. Then you learn better if you do them yourself. So if you connect to the cluster using SSH from your terminal, by the way, again, when you see this dollar symbol in our like pages here, it means connect to the cluster, or use terminal, PuTTY, or your terminal in your Mac OS system. So terminal, I just want to remind you how we were opening terminal like this. Terminal, this black thing here will open the terminal, and then it's gonna ready to connect. And I'll do it for you too. SSH, my username, UMass GHPCC 06 umassrc.org. So when you connect to the cluster, it's going to ask you your password. So when it is asked, just write the password. And when you're writing your password, it's not going to write it to the screen. So we are repeating this because sometimes new people are coming. So when you're entering, it's not going to write anything to the screen. There won't be any star or anything there. So just write it and press enter to log in. And then if you cannot log in, it means your password is wrong. If your password is wrong, to reset, you need to send an email to HPCC admins. Okay, so to understand where you are, like which node you are using, you can always use this name, this command, hostname, GHPCC06. See, this will tell you where you are. So this is your head node, our head node. So, and you can also see it here too. See my username this is the head node. So when you're on head node, sometimes because of the connection or because of something, your child node can drop the connection, and then you can come up to this side, GHPC side. If you remember, if you run things here, you're using more memory and cores here. So you don't want to do that because hundreds of people are using this at the same time. So reaching the nodes. So we are using a job scheduler. So I'm gonna talk about what job scheduler is. So job schedulers, we have lots of different job schedulers, but in our case, in our cluster, we are using LSF. This is like load sharing facility. But before, in our cluster, 7-8 years ago, we were using GSE. It's a different scheduler. Or on Amazon, we are using Amazon Apache Ignite. For example, this is a different scheduler. Or in MIT, there is another cluster we are using it's use they prefer using Slurm. So the reason that there are many different schedulers is because some of them, like for example, this one LSF is from IBM, so they did this. SG is an open source free software. If you want to create your own cluster in the future, you might either use or choose Slurm or SG. They are all open source software and free. So Slurm is a kind of new version of SGE. So the people are they prefer Slurm these days, but we are using LSF in our cluster. So the difference are just the commands. Most of the things are the same. So what they are doing is they have some priority queues. So what this means, I'm going to talk about this a lot today. So what it's just creating a fair share environment in the cluster, because imagine like 100 people came to the cluster and some of the people there are using the cluster a lot. They are going down in the priority list. And if you're using the cluster less than other people, for example, once a week, and every 3 days, it's actually removing you from that queue, that you go to the top of the list if you're not using a cluster a lot. So I was using cluster a lot, and I was always at the end of the queue. And when you are at the end of the queue, it means you're waiting. Your jobs are waiting in the queue more than others. If you are using less, your jobs immediately starts. Or if it is too heavy, sometimes our cluster is too busy, and even your jobs are going to wait. But there are a couple of things you need to learn how you can actually optimize your runs to get one of the nodes in the cluster faster. So today I'm going to talk about those things. So for example, how you're doing is this. Say we have 100 samples sequenced and we want to process them. Imagine you're running them like star. There are some parameters here, and this is my library. Imagine this is one read, single end read file. So when you run the star like this, and if there are 100, if you just submit them like copy and paste, for example, from here, and then submit like this, the next one, the second one will wait the first one. So 100, so you cannot run them like this parallel. So today what I'm going to do, I'm going to show you how you can actually submit these jobs to the cluster, to the job scheduler, and then get your job ID from the cluster, and then wait, because star will take maybe a couple of hours to align your reads if you have like 50 million reads, for example. That's why we need to submit them, and then when they're done, they can send you an email when your job is done, if you want to, because sometimes you submit a lot of jobs and you silence these emails. So how we are submitting the jobs are like this. So there's a command called bsub. Okay, this is the basic way of submitting the job. So what you do, for example, bsub echo LSF. So I'm just going to do this first. I'm not going to use this symbol and first job txt first, but you cannot see what I'm doing. Let's do like this. Just copy and paste here. It's going to be better. So when I do this, enter, it means like, bsub is going to submit the job to LSF. So these codes are whatever you want to run in the cluster. It could be ls, it could be echo hello LSF. Will just write hello LSF into this file, first job.txt. So as you can tell, this file will be generated after this run finished in your home directory. So this was your home, / is going to be your home. So when I press this, enter, I got a couple of warnings. I'm going to talk about what they are. But finally, I get a job ID here. And my job is submitted to the queue. It's the short queue. So we have a couple of queues. I'm going to talk about them, what they are. So in a minute. But it's already written here. So for example, the first warning was no runtime specified. So, and the default runtime is 1 hour. Okay, so this is going to, but this is just going to finish in a second, less than a second. That's why this is not that important. But when you submit the job star without defining or specifying how many hours you want to run that, it is going to be killed. So that's why you need to know how many hours will it take. So you're going to ask me, like, how am I going to know if I haven't run anything before? So first, you're going to submit the jobs to long queue, for example. Long queue means there's like almost unlimited, you can ask unlimited time. And after a couple of runs, you can decide on average, like, for example, if you have 50 million reads, you're going to see that it finishes in 4 hours, for example. Or if it's less than 4 hours, you can always submit your jobs to the short queue. If you decide that your jobs on average is less than 2 hours, for example, you can always submit them to short queue. But I'm going to talk about long queue. Long queue is like, if it's more than 4 hours, you always submit them to the long queue, and you can specify the hour. Like, for example, it's going to finish in 5 hours. You can tell, like in the bold, being in the bold part, you can always ask 10 hours and it's going to finish. You don't want to ask like average hour, like 5 hours, for example, because if it finishes in 5 hours, 1 minute, it's going to be killed. And you don't want to do that. That's why just give a little bit more. Like if it is 5, if on average it finishes in 5 hours, you ask 10 hours. Or if it, if you just calculate the maximum hour for your files, and you can multiply. For example, if it finishes for 20 million reads, if it finishes in like 20 minutes, for example, for 50 million, you can calculate it can finish in like less than an hour. So you can actually do these kind of calculations after you do a couple of runs. And the second thing is the memory requirements. So this is the same thing that when you run, and I will show you how you can look how much time that job took and how much time, how much memory that job used. So you can always look at them to decide how much memory you're going to need in the future. And also how many cores you want to use. Means, I told you, in one node, we have 8 cores. You cannot go more than 8 cores. You can, but you don't want to do that. I'm going to tell you why. But for example, when we run STAR or RSAM, if you run multiple cores, they're going to finish much faster. So this is important. For example, if your job finishes in 8 hours using 1 core, it's not like you cannot divide like I'm going to tell you now. But for example, if you use 4 cores, it's not going to finish in 2 hours, but maybe it's going to finish in 2.5 hours. So because there are some other operations these kind of programs are doing after they finish or before they start or in between the jobs, they take more time. But more or less, when you run like more cores, you are dramatically reducing the runtime. So this is also important, the number of cores. So how we are doing that, how we can define the number of cores, the memory limit, and time limit. See, and the queue. So these are the limits. So this is the maximum memory it's going to use and the maximum time it's going to use. So if you ask, if your job uses more memory than you ask, then your job will be killed. So this is tricky because sometimes your job is using only 1 gigabyte of memory, for example, but in one point of the program, it's using 16 gigabytes. It's not using the average, so it's using the maximum, the limit. So if you submit your job with 8 gigabytes, that job will be killed when it's over 8 gigabytes. So make sure you are asking the right memory and the right time. And there's another command we use to understand all these queues. That first I'm going to talk about the queues. So it's called BQs. So if you just write BQs in the cluster and run, you're going to see lots of queues here. These are the queue names. There are like some people in Amherst, for example, they have their own cluster queues here that they have. For example, they have their priority, and you can see how many jobs are running there. See, this column tells how many jobs are running. And in this case, for example, we usually use this two, short and long queue. And some software like MATLAB or some other software you might use in the future might run better on GPU. So in our cluster, most of the long queue and short queue, most of the queues here are using CPU. But GPUs are graphical processing units. And if your operation requires some graphical processing, then these are working better. So you might ask us like how you can submit jobs to GPU. But we don't have many nodes like this. They don't, maybe a couple of like machines have GPUs, but most of them, long and short queues, you're gonna see that we have more CPUs and more cores here. So here, for example, in the short queue, you can see how many jobs is running now. See, 299 jobs, and all of them are running. There are no any pending jobs. So today our cluster is pretty available. So it's only long. There are some pending jobs, but still it's pretty available. These jobs are waiting. Most likely the same people are running some jobs here, or they made a mistake. They asked for example, more the number of cores they ask more than 8, for example, and then they're going to pen forever here. I'm not saying that they did a mistake here. Maybe they're just waiting because they were using the cluster a lot. But sometimes some people are doing mistakes here, and their jobs are waiting forever until somebody tells them that, hey, your job's in pending state, and it's going to wait there forever. So please change your settings, parameters while submitting your job. And I'm going to show you how you can actually optimize and choose the right settings for your jobs. And in this case, for example, in our long queue, we have 2,688 jobs submitted now, and 193 of them are waiting, pending. Their status is pending, and 2,495 of them are running now. So you can actually check if you think this is, because we have like more than 10K nodes, and this is pretty available. You can submit them to long queue. There's no problem about it. But sometimes, when this is too busy, sometimes you split your files into smaller chunks, because short queue, as you can see, there's a priority scores here. See, 10 to 100. So when you submit a job to the short queue, most likely it's going to dispatch faster. So that means it's gonna start much faster here in your short queue. If you submit to long queue, the jobs are going to be submitted to short queue first, and then they're gonna go to the long queue. By the way, these machines are not different machines. They are the same machines in the short and long queue, but the machines are utilized in the short queue versus long queue. So, but if somebody submits the job to the short queue, and there are other jobs submitted to the long queue, the short queue jobs will start faster. So this priority scores tells you that. So there's another thing you're going to see here, interactive node. So we're going to use interactive a lot. So this is 90. The score is 90. It means when you come to the cluster or head node, we don't want you to use the head node. That's why first you get an interactive node, and then on the interactive node, you can do all your operations. But we don't want you to wait a lot in the head node while when you ask one interactive node, for example. That's why this node dispatches much faster than others. So when you go there, I'm going to show you how we are doing it, but you're going to get this node in a couple seconds usually. So we usually use these 3 queues. Okay, so again, the short queue, your jobs take less than 4 hours. long queue, your jobs take them more than 4 hours. And this is interactive. You can ask how many hours you're going to use, usually less than 4 actually it is less than 4 hours. But when you don't use, just exit from here, from interactive node, even you ask 4 hours, just exit with exit command, and then other people can actually utilize that, so that node, that's core. So what job scheduler is doing, so I changed the names here. This was my name. Another person actually giving these classes, and he left, and it was Hakan, and I changed, and my name was here before, and I changed the names here, but I forgot to change this picture, but sorry about that. But here I changed them with Onur and Arthur. They started giving these classes with us. But so you can read this and understand what is how it is working. But I can tell you the story here. So for example, Hakan says he needs 10 cores, 5 terabytes of memory, and 8 hours of time. Okay. And the system tells that this is going to be a, so this person was a heavy user before. And the system means LSF, this the scheduler we are using, is going to tell Hakan, it's not going to tell anything, but the priority score will be 5 because he was using this a lot. This is what Hakan was expecting from LSF. And Onur asked, like, he needed a 2 cores and 8 gigabytes of memory and 1 hour time. And if Onur wasn't using a lot before, he was a light user before, and the priority score for this job will be higher, 40, than 5. And Arthur comes later, for example. They come to the system in different times. Even Hakan comes first, Onur comes later, but because of his usage was less before, his job will start faster because he's asking less. So all this LSF system is trying to create a fair environment for everybody. So Arthur comes later and he asks 1 gigabyte of memory and 20 minutes. So this is less than this. So and 20 minutes is very short. And sometimes even when you submit this, for example, Hakan is going to submit this to the long queue because 8 hours is more than 4 hours. And it has to go to long queue. And sometimes what's happening when Arthur comes and when he asks very less memory and only 20 minutes, sometimes scheduler suspend Hakan's run. So it waits 20 minutes for Arthur. And then when Arthur jobs finishes, and Hakan's job continues after Arthur, if cluster is busy. If cluster is not busy, there won't be any suspension. So I'm going to show you how you can actually check what's happening in the cluster and what commands you're going to use in a minute. But you can check the status of your job, if it is in pending or running or waiting, like suspended, everything you can actually see. So in this case, when we check the higher, I changed the names here. So Arthur, the higher priority, it was 10. Arthur will be the highest, and Manuel, it's Onur now here. So it's the second, and the first Hakan will be the third. Even he enter, like log into the cluster first. So see, first got in. So first to be dispatched. You were going to expect this, but it is not. So the first, this will be dispatched, and then Manuel, and then Hakan, because of the priorities. So this is how we are using this fair share. Now let's do a more sophisticated job submission here. So I'm not going to do this, but I'll tell you, you can actually write it. I'm going to tell what it is. But so you're going to use the same command, bsub, and -n1. So this is going to ask one node, and the memory is going to 1024. But this one is going to use only one core in a node. So in one node, there will be like multiple runs coming from other people, for example, you're not going to utilize all server to yourself. So you're going to share with other people too. So that's why in our cluster, the rules are not that strict. Sometimes you can go over a couple of gigabytes over your memory usage. It doesn't kill sometimes, you know, according to the usage in that specific node. But be aware there are other jobs there in the same node submitted by other people, and you don't want to interfere their usage, their runs. That's why be aware of your specific runs, specific programs you're using, and how much memory they are using, and then ask enough memory. Otherwise, you are going to use extra memory, and then this might interfere other people's jobs, and then they might they might be killed also if they are in the same node like you are. So that's why when you don't use the whole machine, you have to be aware that you're sharing the machine too. This is the how you can actually change, like -R. This is the R usage. Like memory is equal to 1 gigabyte. This is 1024. If you want to increase this, you can do 2048, whatever, 2000 only, or 10,000, around 10 gigabytes. It doesn't have to be specific. But you know, you just give something that, a little bit larger than you might expected about that specific program. And this -W is the number of minutes, like how many minutes you're going to use. So this is going to be 20 minutes. So if you do this like 120, it's going to be 2 hours. So and -Q is going to be the short. And if your job is going to finish like in maybe 720 minutes, just submit them to the long queue. Just change this -Q to long. This short is not going to be the short in long. So if in the future, if you go to another institute, they might not use exactly the same naming of the queues. So learn these things from them. And this is your job, whatever you want to run. In this case, you're writing them into this codes, and sleep 300 will do the this is going to run 300 seconds, and your core will sleep. Just run this and see. So what's happening, and watch. Maybe I'm gonna do this too, just to show how it is doing, and show one more command, and I will give you the rest, and then you're gonna do it, and then I'm gonna talk more later. See, I submitted this, and it's gonna wait 300 seconds, and the job is here. And when I do this B jobs, I can see my jobs. See, this is my short queue. This is I submit this from this host, and this is GC35B15, and this is the job name, and this is submission time. So this is still running. See, when I do this, the status will be running. So B jobs. So when this is done, when you do B jobs -A, you're gonna see this. See, this job number is here, and when it's done, it's gonna come to this list. And when you do B jobs, it is going to be removed from this list. So when you do B jobs -A, you can see what happened to the job when it is finished. And if it is done, you're gonna see done. If it is zombie, means this job is something went wrong in this job. You need to understand this kind of zombie jobs, or unknown, or killed, or error kind of jobs. You have to look at this list. If you see this kind of if it is not done, it means this job is not successful. So you have to track all the jobs, see them, look at their results, and then resubmit them if they didn't run right. So, and another thing I want to show you, B jobs -L, oops, -L, the job number will tell you more details about this job. See where it is submitted, which host it used to submit, how much memory you asked, and which node actually it used. This is the node name. I'm going to talk about that too. And how much memory it's used, and CPU, how much CPU you asked, and these are the limits, and this is the memory limit. And then you can see how much maximum memory you used. And if you see this number is larger than 1, if it is not killed, next time increase your memory. So you can learn all these scheduler parameters, their scores and everything here. And all the information is here just when you want to optimize your runs. So how I did was bjobs minus L and the job ID. So how you get the job ID? Again, when you do bjobs, this is the job ID, first column. And one thing, you're going to do these things yourself to understand. If you want to kill the job, you can use the bkill and the job ID. You can do that. But I want to show you this interactive one before. You're going to do this yourself, but I just want to show this interactive job. See, I'm using the head node. So the first thing you will do when you come to the cluster, I suggest you to just run this command, bsub minus q interactive. And this is 120 minutes, 2 hours. And this is going to be the shell that I told you, maybe I showed you last week. This is going to open use a bash there. So when I enter, see dispatch immediately starting, and I'm there now. See I'm on that. Let me do host name. See C40B04. See, I'm not on head node anymore. So the head node was like this. When I log in, I'm like this now, bash 4.1 host name. When I run the host name, I see which node I'm on, but the same things are working here. Like, see, I have one running job and one interactive job. Okay. So if I want to kill this, see, I can use bkill and this job, see, this being terminated. So when I do bjobs minus A, see, I see this job exit. So this is not finished successfully because I killed. You can kill yourself if you're not happy with that job. And what you can do, you can rerun. But this can be killed by the admins too. Sometimes they see that you're doing something wrong, they kill. Or sometimes you are using more cores than you asked, and then it's going to be killed. Or sometimes you're using excessive memory, they're going to be killed. So when you do this, bjobs minus L with this specific job, you can see the reason why it is killed. See, completed exit term owner, job killed by owner. So because I killed this. But then if it is killed by the admins, you can see job killed because of the memory or job killed because of the course. Then what you do is just to understand the reason and then resubmit the job by asking more core or more nodes, more memory or more time. Okay, so now I think we are done for this. I want you to finish this yourself and do the homework now when we're here. And we are gonna be back and then read the things here because I skipped lots of things. I want you to understand everything here. And we're gonna be back in half an hour. You can take 5 minutes break before you come. Let's start around 10:30. Unless you have questions, you can do it yourself, all these things, and then I'll move on other things after 10:30. Okay. Any questions?
I have one question. So when you schedule the memory that you need and the running time, are they limited by availability of your memory on your project? Or I mean we have
Yeah.
okay.
Continue, please go on.
Yeah, I think that's it. That's what I wanted to ask.
Okay, so they are not limited to your project, but when you submit the job, usually you are using a program like Star or FastQC or a Perl code or something. So if it is written and published code, for example, like star, for example, we know more or less how much memory they are using. For example, star is using a lot of memory. And when we submit job with star, we usually ask 32 gigabytes because it is trying to put almost all the genome to the memory, and it's extremely fast. But there are other software. Sometimes you're writing yourself a piece of code and you don't know too much about memory usage. And for example, you do something wrong in your program and it's using, for example, 100 gigabytes because there's a memory leak in your code, for example. You have to know what you're doing while you're coding. Unless you know, sometimes you can actually create a program has these kind of problems, and this might be a limit of your code. But when this code is written and used a lot, like star or fastqc, more or less we know how much memory they are using, and then we ask that much memory. So you can ask us, for example, star, you can ask us how much memory we are using. And in Dolphin Next, we already set this up for you. There are some default values for them. 99% of the cases, they are working pretty well, but sometimes some people are coming and they are using like 1 terabyte of FASTQ file, for example. In that case, we increase the memory usage to 64 gigabytes. Or some programs are like using a lot of memory if they have like Java component inside. Java is using a lot of memory. We know that Java is using a lot of memory. Sometimes we are increasing the memory to 128 gigabytes. But there are things that one more thing I have to tell you, these machines have memory on them. So this is also a limit. So these machines that one node has, for example, half a terabyte memory. So if you ask more than half a terabyte, then your job will never be dispatched. So this is something, a very hard limit. So what you do, some software allow you to run them, that software in multiple nodes. So you can ask like 16 CPU, but you have to know if that software allows that or not. Some software doesn't allow that. So you have to submit the job into single node. It can use multiple cores in a single node. So there is another command I haven't written here, but these are advanced usage. So I can tell you if your software needs more than like 256 gigabytes, for example, it's rare, but if it requires this much, let us know. We're going to help you and tell you how you can actually submit jobs to multiple nodes. But this is like 1 out of 1,000 case for us. Very, very less rare case. We usually utilize like, single job in a single node, multiple cores. So if you do like this, your job will be dispatched faster and you're not going to wait much. But one more thing, one more trick here. If you ask more like 8 cores in one node, so this means the whole node has to be empty that your job will be dispatched. Means none of the jobs will be there on that node, specific node. So this is if the cluster is busy. This is also kind of hard because because of the priorities and everything, the new ones are coming and they're not using cluster a lot, and then they get 1 core in the whole node, and your job can wait a lot if you ask 8 cores. That's why I suggest people just don't ask more than 4, max 6 cores in a node, and then there'll be 1 or 2 cores can go to other people, and then you can your job will start faster, will be dispatched faster. So that's why there are these kind of tricks. In the future, when you start using a lot, you're going to understand these things, because you're going to see some of the jobs when you ask 8 cores in a node, it's going to wait like a day, because your priority will get higher and higher when you're waiting, and also that it's going to find that time that whole node got empty, and then it's going to dispatch your job. But again, we never do these things. We always ask less than 8, like 4 max, or 6 sometimes at most, but then our jobs are never waits unless cluster is too busy. So these are the tricks.
Thank you.
Any other questions?
Alper, when you say it's one node, is that the same thing as one host, or is that different?
Yes.
Like when you do -n and then the R span.
It's actually in RSAM when you use -n, you know, in old times we had one core in one node before. So that's why they always say -n, but it's actually it's using the core. So if you say -n4 in RSAM, it's going to use 4 cores. So it's not going to use 4 node. Node means the whole machine, whole box, whole server or host, that child node. But that child node usually has 8 cores. So you can use this when you're using RSAM or star, you can use -n4. Then it's going to be good on that specific host. Okay, it's the host. But I'm using like node is the whole machine, whole host. Core or CPU means the number of CPU is the same like I use like the number of cores. So one CPU is equal to 1 core. But sometimes, sorry, it is not in actual world, by the way. When I use like this, again, I'm thinking old times. In old times, there in one CPU, there were only 1 cores. But today, for example, in my computer, I have like 1 CPU, but that CPU has 4 cores. So they also added more cores into the CPU. But core means like in one CPU, if there are 4 cores, you can do 4 parallel jobs, or you can submit 4 parallel jobs onto the same core. And also when you use -n4, it's going to use that one single CPU, but 4 cores. Okay, it's gonna run parallel. So think about like this. Is it clear, or you want me to repeat?
So what about when you use the command like -n and then RSPAN, like R span, and then a number?
So
because
yeah,
that specifies the hosts, right?
Exactly. So the R span is that. So if you push R span is equal to 1, it is going to ask all the cores have to come from the same node. Okay, so they're gonna come from the same host, so on the same computer. But some software, that's why most of the time I push this R span is equal to 1, because many software don't allow running them in different nodes. Okay, so you have to know that software allows running them in different nodes. So
I see. Okay, and then
yeah.
Okay, and then my second question is, when you say, like, for example, if star needs 32 gigs of memory, and you want to use 4 cores, then do you set 8 gigs of memory per core, or do you ask for 32 total, or 32?
No, exactly. So you have to divide to 4. If you ask 4 core, if the total memory is 32, you have to ask 8 gigabytes, because it multiplies 8 with 4. So if you just give 32 again and ask 4 cores, it's going to multiply 32 by 4. So it's going to ask more memory than you need. And then it's going to dispatch, yeah, slower. These are perfect questions. I love your questions. Thank you. Okay. I'm just going to take a break myself, 10 minutes. So you can finish, and I'll be back in 10:30. Okay.